Before we dive deep into the CFD analysis and the governing equations, we would like to review some of the basic vector terms that we will use along the upcoming topics. As we know that scalar is give you a quantity, right? A scalar value, it just gives you a quantity, a sensation of the quantity, but it doesn't tell you a direction. And to be able to look into the direction, you have to convert that scalar value or scalar function into more vector function. And since in fluid mechanics, we are interested in knowing the information both on the scale value, on the direction value as well, or direction as well, it is very important to start using vectors into CFD analysis. So there are standard, they call it the operators or standard processes that we would use more frequent into the analysis of CFD. So let's just review 4 or 5 of them. That's what we're going to use in most time. So let's assume that we have a scalar function f. So this gives us a value, a sensation of a value. It could be actually a function of x, y, and z. So this could be actually function of x, y, and z, right? But still, it gives you value, but doesn't tell you anything about the direction. How we can convert that scalar function into direction so we can get some information about the direction. For example, I told you that the fluid velocity at that location x, y, z is 5 meters per second, but I didn't tell you, is it going into the x direction, into the y direction? It's tilt with a specific angle to one of the specific axes. So that's very important for us, right? So how to convert that scalar function into a vector function? This is where the nabla operator comes in. Nabla operator usually takes the inverted triangle, and again, it has the ability to convert a scalar function into a vector function. What's nabla? Nabla is a vector of derivatives. And I know that vector can be written in a different format, so I can say that nabla is partial by partial x, comma, partial by partial y, comma, partial by partial z. That's a one way to write the vector format. The other way to say that nabla is simply partial by partial x in the direction of I, plus partial by partial y in the direction of j. You can put the hat or not, partial by partial z in the k direction. So either way is presenting that nabla operator. So now f is scalar function, and now I would like to apply nabla. So nabla f, it's simply the partial of that function by partial x in the I direction, plus partial of that function in the y direction or j direction, plus partial of that function relative to the z in the k direction. So that's how we write down the nabla of it. Now this is becoming a vector, right? It has I, j, k direction, so it's telling me about the direction of that scalar function f. So that's one operator. Sometimes we call that nabla f, or sometimes we call that the gradient. So nabla or gradient, they both do the same. So gradient of a scalar function is nabla f, is the vector coming out to present the derivatives of that scalar function. The second most commonly used term into the CFD work is actually the divergence of a vector. Okay, and simply the divergence of a vector, div, that's how we write it down. So let's say that I would like to get div, division of a vector f. It is simply the nabla dot product of that vector f. that's the so if here is a vector, and it's simply the dot product of the nabla operator and that vector, which means that dot product is usually give me a scalar value. So the divergence is converting vector into a scalar value. Okay, so let's assume that nabla is, by definition, is partial by partial x in the I, right? I'm going to write it in that format. So it's partial by partial x, partial by partial y, partial by partial z. Let's put that f, whatever that f of x, y, and z. So I would get the divergence of the f will be simply partial f by partial x plus partial f by partial y. Remember, f is function of x, y, and z plus partial f by partial z. And you notice that this will end to be scalar value. Divergence is really very good to give you some sensation about the fluid flow. So if the divergence of a vector f is positive, it's telling us that the fluid is actually diverge out, which means that you have a source and the fluid is going away from that source. That's if the divergence is positive. If the diversion is negative, it's telling me that the fluid is sinking in specific point. So if the divergence is negative, it's telling me that, hey, your fluid is sinking into a specific location. So if the divergence equals 0, it's neither conversion or diversion, so which means that the fluid is moving in a parallel to, streamlines are moving parallel to each other. So that's simply what we can gain from applying the divergence of a vector in fluid mechanics. The next and very famous term or operation or process that we will do in fluid mechanics, the Laplacian. This would be the next one. Laplacian takes the symbol delta, or it's actually the nabla square, and Laplacian, it's simply the diversion of the gradient of vector f. Okay, so that's vector, and Laplacian will be simply diversion, which means that it's nabla dot, but this time it's not going to be directly the diversion of the vector. It's going to be diversion of the gradient of that vector f. So I'm going to end up having a scalar value. So if I break down, nabla is partial by partial x, partial by partial y, partial by partial z, dot product of partial f by partial x, comma, partial f by partial y, comma, partial f by partial z. So you will have partial by partial x of partial f by partial x, which simply can be written as partial 2f by partial x squared, and the same applies for the y, same applies for the z. So I'm going to end up having just a scalar value. The last operation of interest from the vector calculus is actually the curve of a vector. It is simply give me another vector, and the curl is simply is a cross product of the nabla cross product of that vector, and the curl give us the information about the rotation of the fluid. So for a specific sign of the curl, you may get the sensation of the fluid circulating clockwise or anti-clockwise. So that's the beauty about the curve. It tells us about the fluid rotation. So the divergence give you the information about the convergence and divergence of the fluid to a point or from a point, and the curve give you the sensation of rotation of that fluid around the point in any direction, clockwise or anti-clockwise. So the curve of F is simply can be presented by the cross product, and we know that cross product can be done in the matrix format. It's partial by partial x, partial by partial y, partial by partial z, and we will have fx, fy, fz. These are the three components of that vector f. Then you can break down that in the I direction. I will have partial fz by partial y minus partial fy by partial z. This is in the I direction. Minus in the j direction, I will eliminate the row and the column. So I'm going to have partial fz by partial x minus partial fx by partial z. This is in the j direction. Plus in the k direction, I would have partial fy by partial x minus partial fx by partial y. This is in the k direction. So I end up having a vector at the end. That's the most operators and the processes that we're going to do in fluid mechanics. The other important thing is actually the chain rule, how to do the differentiation using the chain rule. This is also another thing that we would like to be remembering it. That's I think that's the right word to say. Everyone as a mechanical engineer should be able to do that. And as an engineer in general, doesn't have to be mechanical, but let's assume that we have a function W. So I'm going to call that chain rule. If you have a function W, that's function of a variable G, but you know also that G itself is a function of X. So I can write down that W is simply a function of G, which is itself function of X, right? So there is dependency here. W depend on G and G depend on X. So any change in the function W should be partially changed with G, because G itself is dependent on another variable times the total change in the variable X. That's how the, that's dG. Okay. So dW is partially changed with G time whatever it's happening here as a total change in the function G. Okay. And why it's D, what's the total derivative? Because G only depends on X. What's partial for the G? Because W changed relatively to G, and G is depend on another variable X. So it's partially depend on G, okay? There is dependency, there is down dependency on another variable. We call that actually a single level or one level chain rule. So if you want to get the variation of W relative to the variable X, it would be simply partial W by partial G times dG by dx. So that's the one level chain rule. What if we gonna go deeper? So for example, we said that velocity may be changed as a function of x, y, and z, right? And the time t. So for example, if we have W, that's function of x and y, but we also know that x itself is function of the time t, and y itself is function of the time t. So the diagram I draw is always simplify the problem. So W will be fed by the variation of x and y, but also x and y both will be fed by the variation in t. So this is the end of the variation, right? X is ending to be function of t, so that's dx by dt. Or you can call it dx for now. This is going to be dy by dt. But w, because it's more dependent on different levels, this will be partial w by partial y, and this will be partial w by partial x. So if you wanna get actually dw will be partial w by partial x times the variation of the x plus partial w by partial y times dy. If you want to get dw relative to the time t, this is the end variable here. It will be partial w by partial x times dx by dt plus partial w by partial y dy by dt. So that's a multiple level chain rule. We use the multiple level chain rule to define something called the material derivative or the total derivative. So you remember when we talked about Lagrangian and the Eulerian approach to describe the fluid flow, we said in the Lagrangian that velocity it will be function of x, y, and z and t, but also each x, y, and z component will be also function of time. So I would say that velocity will be x, y, z, and t. These are direct variables here. But also x, y, and z itself will be impacted by the time t. So if I look to the first level of variation here, I would have partial v by partial x. I would have partial v by partial y. I have partial v by partial z. Then I have direct change dz, right? And this is, that's dz, that's dy, and that's actually dx. So if you want to get the variation in the velocity, there is a direct variation for one level here, so that's partial v by partial time t. So the dv, based on all these variables, will be simply partial v by partial time t plus partial v by partial x dx plus partial v by partial y dy plus partial v by partial z dz. If you want to get the variation of any parameter alpha, will be partial alpha by partial t. I'm trying to generalize it right now, plus partial alpha by partial x dx plus partial alpha by partial y dy plus partial alpha by partial z dz. Okay, let's assume we would like to get that variation of that function v or function alpha relative to the time. So d alpha by dt will be, first term is not going to change, plus partial alpha by partial x dx by dt plus partial alpha by partial y dy by dt plus partial alpha by partial z dz by dt. So d alpha by dt is equal partial alpha by partial t plus dx by dt will give me u, dy by dt will give me v, and dz by dt will give me w, whereas u, v, and w are the component of the velocity vector, u, v, and w. So I end up having d alpha by dt equal partial alpha by partial t times u, partial alpha by partial x, plus v, partial alpha by partial y, plus w, partial alpha by partial z. And we call that actually the total derivative d alpha by dt, that's called the material derivative, or sometimes we call the total derivative. Okay, so d alpha by dt, this is how we call the total derivative. D capital is simply the variation of alpha relative to the time plus, right, vector v dot nabla v. Remember, v is u, v small, and w. Dot nabla v is partial u by partial x, or d alpha. So partial alpha by partial x, partial alpha by partial y, partial alpha by partial z, right? So when you do the dot product, it's going to be u partial alpha by partial x, which is that first term, v partial alpha by partial y, that's the second term, and w partial alpha by partial z. So this is a short handwriting notes or the equation of the total derivative. If we are doing the total derivative of velocity rest to the time, I would have partial v by partial time t plus the velocity vector v dot nabla v itself. And we know that the total derivative here of the velocity relative to the time, this will give me what? That will give me the acceleration vector. So the acceleration is the total derivative of the velocity to the time. And you will notice here that I have partial v by partial t plus, if I break down that, I will have u partial v by partial x plus v partial v by partial y plus w partial v by partial z. This seems to be the variation of velocity relative to the time. So we call that actually the local acceleration. So at given location, this is the term presenting the variation of velocity relative to the time. But we have a second term of the acceleration. It's called the convection acceleration. What does that mean? It means that it's the variation of the velocity with position. So the local acceleration is variation at fixed location relative to the time. While the convection acceleration is the variation at given time relative to position. And that's give me the total acceleration. So keep in mind, there are two components of the acceleration, of the fluid flow acceleration. There's a local acceleration, that's the variation of velocity relative to the time at a given position, while the convection acceleration is the variation of velocity with the position at given time. Okay, so that's how we look to the total or material derivative. So I'm going to call that material derivative, and we use that material derivative to derive an equation. This is very important equation for the breakdown of the equation to the acceleration of a fluid flow. So this is a key equation that we're going to need when we look to the conservation equations.